We've all been there. You're about to throw your banana in the air when you get the sudden urge to predict how it's gonna spin. In this lab, we turned a banana into a simple pendulum and analyzed its motion to find its axis of rotation in two ways. First, using the radius of gyration, and then using the center of mass. We then threw it and assessed how accurate our predictions were.
Our plan involves 3 steps. First, we find the radius of gyration by turning our banana into a simple pendulum and measuring its natural frequency. Second, we find the center of gravity by suspending it in 2 axes and identifying the intersection of balance points. Finally, we throw the banana with spin and observe the actual axis of rotation about which it spins. We expect the center of gravity to be the axis of rotation, but we will evaluate how well each prediction method works.
To determine the natural frequency and radius of gyration, we created a banana pendulum with a pencil stabilized through 2 bearings. By attaching the banana stem onto the pencil, we could swing the banana and count the number of swings and read the time interval. We analyzed the motion through multiple trials of different numbers of swings, and by assuming a small angle approximation, no air resistance, and no friction in the bearings, we could determine the frequency of the banana.
We approximated the banana as a point mass on a massless rod, so the length of the rod is the distance from the axis of rotation to the center of gravity of the banana. We used the simple pendulum formula omega equals the square root of g over L, where L is the radius of gyration. We then marked this point onto the banana using calipers.
Next, we found the center of gravity again by hanging the banana and marking the point on which it balanced. We already knew the point should lay along the plumb line of the hanging banana, which gave us one axis, so we hung the banana perpendicularly on a new string and marked where this line intersected with the plumb line. We noticed that we could balance the banana on a range of points, so we identified the extremes and marked the midpoint as the center of gravity.
We marked the banana with points. 2 of them are the reference points. 1 point is the center of gravity from our balance testing, and the last is the radius of gyration from our pendulum swing approximation. We tossed the banana upwards while spinning it and observed its motion. We expected that at the top of the parabolic path, the axis of rotation would be very clear.
We derived an equation to calculate the radius of gyration of the banana by putting it in a perturbed position. Using our estimated angular frequency and the distance to the center of gravity from the axis of rotation, we found the radius of gyration. This way, we can estimate the mass moment of inertia of bananas with similar shape and makeup if we ever want to rotate any more bananas. Our results are limited because there are many factors we have not considered. We assume that the frequency we measured was a natural frequency when it is in reality the damped frequency due to friction. Our massless rod approximation is also not entirely accurate because we assumed the banana as a point mass on a rod. Also, our balance testing is not entirely accurate as well since the banana might have balanced on the string due to friction. That is why there is a range on the center of gravity and we took the average within that range. And the radius of gyration cannot be used as an exact value since we have only tested it with one banana and cannot be generalized for all bananas.